Aspera and IBM company is their first time presenting at Discovery Track. Please welcome Mike Flathers to give us Can't We Do Better Than TCP? Take it away, Mike.
Thanks. Hi, everyone. As Troy mentioned, Mike Flathers, Chief Technologist for Aspera Developer Platform. I just want to preface things by saying, I've got quite a few slides. We're going to blow through a bunch of them here because there's more here than we can talk about. But I just kind of wanted to give some of the techies in the room a little bit of a flavor for some of the things we can talk about. If you want to get into the math behind everything as well, because we can actually prove out what we do. At any rate, so we're gonna talk today about some of the challenges for live streaming over the internet, and in particular, packet loss and delay or distance, play a major role in what you can achieve. Then I'm going to talk a little about fast stream software. We're going to look at some of the performance characteristics of both the fast protocols compared to TCP-based technologies, such as HTTP, Dash, and so forth. And then we'll look at a couple of use cases, just very briefly touch on those. We've got a couple of demos here that we can walk through, which will probably be the fun part for everybody. Then briefly talk through some real world examples. So we all know that some of the big challenges for live video, transport. A lot of us in here have dealt in the broadcast world for some time. And satellite equipment is very expensive and kind of impractical for some of the venues that you may want to do a live feed from. So. What we've done is we've tried to make it so you can actually use commodity internet, so to actually transport very high quality video over just kind of public internet connections. Obviously satellite equipment is very difficult to integrate with modern cloud environments. We operate both on premise and in cloud. Our software is exactly the same no matter where you are. We're software only, so we have no hardware component to what we do. We run with commodity hardware, and you'll see some examples of that. Some of the more obvious things, disproportionately expensive for long tail content, and when we start looking at some of the TCP-based technologies that have been developed, of course, we're all familiar with things like HTTP and adaptive bit rates, RTMP, some of the standards that are out there. They start really collapsing over wide area networks. Anytime there's packet loss or latency that occurs, and I'll talk a little bit about that in a little bit more detail on the next slide. And we can talk about some of the math behind all of this. Just on the right here is just an example of some work that we've done, just kind of just for points of reference. I mean, there's a lot of data and a lot of streams that we're pushing through, and of course for things like the Olympics and World Cup and those types of things, the quality has to be very good. And if you look at this bottom bullet point here, for 10 megabit streams times 24 times 2, it's about 480 megabits in aggregate. Again, going into cloud workflows as well. Again, adaptive bit rate, of course, reduces the bit rate and lowers quality, and of course the user experience as well. So you want to keep that bit rate as high as possible. I'm going to be talking, solely to the transport layer here today. So that's where we operate at. Is again, like I said, we operate with standard hardware out there, commodity hardware that and support all the standards that are there to move data. And in fact, I know we're at a video conference here, but the data to us is transparent. So we just move the data from one point to the other as fast and efficient as possible. All right, so to compare and contrast a little bit, forward error correction over UDP, FEC technologies actually have quite a bit of overhead that is introduced, just by the nature of how FEC works, and we've been told by customers that in their real world use cases that forward error correction technologies actually at kind of a moderate bit rate of say 10 megabits a second actually and kind of just intercontinental distances, they actually required to send about 25 times more data over the network than you have to with Aspera. So there are really big differences, and it just has to do with the nature of how things work. With forward error correction technology, of course, extra data is sent to make sure that you can recover from what gets lost during transmission. But with us, we have more of a negative acknowledgement kind of scheme that's very fast and efficient. Our rate controller is one of the pieces that is, I would say, our secret sauce, right? We put a lot of effort into our rate controller to make sure we can hold you at the bandwidth that you say you want to operate at, and also just do things like set policies, so minimum rates, target rates, policies such that you can how different transfers will interact with each other, on the wire. We're constantly monitoring what's going on the network between the two endpoints to make sure that what we do is keep things in check all of the time, so we don't overdrive the network. And then, of course, for us, it's all about efficiency. The whole path, not just how fast can we transfer over that WAN part, how fast can we ingest, how fast can we actually output as well. And then we support. Most of you probably know us for our file-based workflows and the protocol working with files. And of course, for those type of environments, how fast can we read from storage and write to storage becomes really important as well. And I just mentioned that because there are a lot of workflows out there that are either stream to file or file to stream based workflows that we work very well with. I'm not going to go into a lot of the math today. We can talk about it if you want to find me after at some point. We're happy to talk about it because we've got a lot to show today. Again, the one of the big things about us is given the bandwidth, we're very predictable. You can count on being able to deliver at a rate that you can actually calculate based on available bandwidth. So let's take a look at a couple of key features of FASP. And I'm going to mostly talk to the graph here. So what happens is, as latency, round trip time starts increasing along this axis here, and as packet loss starts to get greater along this axis here, TCP-based technologies start very much degrading, and that's because TCP wants an acknowledgement for every packet that it sends, and what happens is it'll artificially start shrinking what's called a TCP window size down to artificially constrain your bandwidth to make sure that it has a good chance of actually obtaining, getting an acknowledgement for every packet it sends. So in these real-world environments, here you can see that TCP in the yellow starts, as you get greater distance and you get greater packet loss, you can see that TCP-based technologies like HTTP, FTP, and those kind of things really start degrading significantly. Whereas FAST, basically, we're your effective bandwidth just minus any packet loss that may occur. So we're very, very efficient in that regard. And it's the same technology. I want to make a big point of this. It's the same protocol with FAST Stream that we're going to be talking about today that we've used with our file transfer-based technology, that you're probably all familiar with. Again, I said I'm not going to talk about, we're not going to go into probability theory here, but we have some, again, we can prove things out mathematically. Again, I'll skip this slide as well. So let's just take a look at a fairly decent bit rate at 40 megabits a second here. If we look at the probability of actually getting a glitch, which is is one, losing a piece of data over the course of an hour at a fairly high bit rate. It's 40 megabits. If we just buffer just a little bit, say sub half a second, you can see they're pretty much guaranteed to get a glitch with just about anything. It's gonna, and it's with FASP. And then as we kind of have more buffer time, of course, that significantly drops off, ending with, bad wireless satellite connections. We can still perform, fairly well with fairly low amounts of buffering. Okay, this is just the same slide at 20 megabits a second. You can see how things, start becoming even, a lot more less likely to actually achieve a glitch. 10 megabits a second, same thing. and down to 5, and then 2, and then 1. Well, let's kind of hold there for just 1 second and let you look at that. So even under some of the worst conditions, bad wireless satellite, 500 milliseconds of latency and 5% packet loss, we can still pretty much guarantee that there's a very, very low probability of receiving a glitch with FAST with around a second and a half of buffer time. Okay, this one we kind of turn things on its head, and we're kind of looking at how much do we have to buffer. It's kind of that the previous slides kind of in reverse. So at these higher bit rates, the initial buffer starts at the higher bit rates. We have to have a little bit more buffer lead time there. Now, if we compare this to TCP-based technologies, you can see here that and this on the left side is the percentage of the bit rate that you can actually achieve at these different rates given these different conditions. So you can see that TCP, you start getting out of these higher bit rates, can only achieve a very fraction of what our fast stream protocol can achieve. So just kind of talking about some of the advantages, I've mentioned several of them already. Predictability, again, very, very important, especially as you do capacity planning and things like that. We're, as I mentioned, we're independent of distance, so we're independent of packet loss, independent of round trip time or latency, and even under the worst conditions, we can actually obtain nearly a zero startup delay. And I'm going to show you a couple things that'll bring this home, and you'll see the evidence there. And then again, we don't use forward error correction. We have a very efficient scheme to actually make sure that we only transfer the minimum amount of data possible to make sure we provide a glitch-free experience. Excuse me. Again, predictable. You can determine the rate that you need to set things at to be in a very statistical manner to achieve your ideal rate. Again, we're not reliant on sending redundant data. We're reliant on basically recovering from what did not make it again very efficiently. And then of course that all points to very low probability of buffering. And one thing I should mention with Fast Stream is that what we do is we can actually take in. We work with commodity hardware. We can take in UDP unicast or a multicast feed. Also, and TCP as well, and we emit the datagrams exactly how we receive them on the remote side. So we take them in on the receiving side, transport them, bulk them up and transport them over our transport, and then push them out on the sending side. Now I know, how much time do we actually have here? But another 10 minutes or so?
Hold on just a second. I
want to make sure we get to the demo portion.
You have 7 more minutes.
Okay,
We're
perfect.
a little late.
Perfect. Okay, very good. So again, here's just a slide that summarizes everything we've talked about. That get at these different some of these lower bit rates, we can go a long time with sub 1 second startup delay, without seeing a glitch. And this is based on not only theoretical numbers, but we also have the lab numbers to prove this. And I've got more elaborate details that I could go over with you at some point. This is just a scatter diagram that actually just shows you, and this is results from real world. I think this was. I'm trying to remember what the conditions were. I think it was like cross-continental, 100 milliseconds of latency, 1 or 2% packet loss. And the light colors is where we miss something. The white is where we miss something. Okay. I'm not going to talk a lot about how we package things up, but again, like I said, we support workflows for stream to stream, stream to file, file to stream, and there's several use cases that we're applicable in. And as you can see, from a capture standpoint to a broadcast to a playout facility, from just live ingest and transcoding and redistribution and those kind of things. I'm going to briefly talk about something. This was a slide from, I think, IBC this last year. One of the things that we did was we had a workflow where we used, again, commodity hardware with several of our partners, and we actually, pulled in a live stream, actually brought it into Dublin, Ireland, somewhere in Europe, close to Amsterdam, and we did some real-time graphics overlays there, and then pushed that out, at the show floor. So in that case, we pulled from New York, but we actually had feeds from China, from Utah, from other places around the world. We also, like I said, pulled this feed in from China. I'm going to skip this one for today. Maybe we'll go to it, but just there's another one that I want to show you here. We also did some auctions with Meekum and worked with NBC Universal on a couple of things where we had pulled live streams out and pulled confidence feeds back. Or again, it's all public and it's all fairground internet, and they were beautiful streams. In fact, you can see traditional satellite equipment that was there. We replaced it with this, and just a subset of this actually. And by the time we started the event, the first event, the truck guys had pulled us into them right next to them, the internet confidence feed, right next to the satellite confidence feed. I'm just going to maybe show here. Let's see. Kind of what this looks like here. I'll just kind of roll ahead. You can see this is our internet confidence feed next to the satellite confidence feed that they pulled right next to them. We're close to a second ahead. I'll pull that back so you can actually see that. So you can see how far ahead we were. Don't want to spend too much time here, but that was a good example. Now I know we're short. We're a little bit short on time, so there's one thing that I want to show you here and compare us with fast stream as compared to standard HTTP. And this is actually we're pushing dash segments here. And if I go ahead and play, what you'll see here is it's the infamous Big Buck Bunny video, and on the left side we have HTTP. On the right side we have fast going. Now they're going to start out about the same because Dash is going to start at the lowest bit rate first, but you'll notice what happens here is HTTP start at a lower bit rate, and we start going up, adaptively going up to higher resolutions, and also our stream rate is significantly higher as well. This is I'm just on standard Wi-Fi that you are all on. So if you compare the left-hand side to the right-hand side, you can see the video quality differences and kind of see side by side how fast our fast stream technology compares to standard HTTP. So I will, this will wrap up. It'll probably jump to 1080p. There it is, here. And again, if you compare kind of the left side to the right side, you can see how much better the quality is. Jump back to the presentation really quickly here. We've done this over some great distances. We did it. Here's an example of an event from Havana, Cuba, pulled into our Utah office. Our Utah office is the office that I'm located in. One of our windows actually looks out at this NSA building. It's a 1 million square foot data center, and I had visions of someone knocking on my door because we were pulling in all this data from Cuba directly into Utah. But at any rate, it didn't happen. It was actually pretty poor network condition. 12% packet loss, and it was John. What was that? 8 megabit stream, 7 megabit, 4 or 5? I can't remember. 4.5. So we have real world, cruise ship. I did this on a cruise ship as well. That's the equipment I brought with me on the cruise ship. Got a 10 meg feed that we actually pushed into NAB East this last year as well on the show floor directly from a cruise ship in the middle of in the middle of the Atlantic. Jumping back here, this is what I want to end on. At IBC this last year, we had a press event. Had a stream going from our Utah office into our booth, directly into our booth in Amsterdam. Okay, public internet, show floor internet. I had someone come into the office, do a 5-finger countdown. I had them on my cell phone, so the audio was coming from my cell phone, 5, 4, 3, 2, 1. The video was totally in sync. In fact, the last line, why I separated it, is what I'd like you to focus on. That one of these reporters said the delay was imperceptible, and it truly was. It was as if you were there. So with that, I want to thank you all for joining me today.
All right, round of applause. We have time for one question for Mike, if anyone has one. Do we have one question? All right, we got one question, Mike. Hold on.
I'll let you answer it maybe, but.
Can you just explain the difference between a startup delay and a buffer delay for the audience?
Answer that.
So startup delay is how much time it takes to actually start playing, whereas buffer delay is how much time it takes to actually to continue playing.
Okay, everyone, that's time. 10-minute break. We'll be back.